All right. So good afternoon, everybody. So we are very happy to have Dr. Tanmoy Modak as a speaker for his afternoon seminar. And Tanmoy did his PhD at Math Science with Rahul Sinha, and then he spent a few years at NTU, National Taiwan University in Taipei, working with George Howe. And for the last 1 year, he has been at the University of Heidelberg, and he mainly works on flavor physics and Higgs beyond standard Higgs physics, especially particularly beyond the standard model Higgs searches at LHC and other colliders. And today he will talk on baryon asymmetry, what is called probing the origin of matter-antimatter asymmetry at collider experiments. On one.
Okay, thank you. Thank you for the nice introduction. This is a very simple talk, and most of you already know what it is, and I'll explain this thing in a very simple manner. And the model I'll discuss about is also pretty well known. My apologies in advance if I miss your references. Just please remind me so that I don't miss in future. And you can see my mouse pointer, right?
Yes.
Yeah. Okay. So these are the works that I have done in last 3 years, and mostly related to baryogenesis or matter-antimatter asymmetry of the universe. I interchangeably use matter-antimatter asymmetry, baryon asymmetry, or baryogenesis. Okay. And my collaborators are Professor Oishu Hao. So he was my former boss, postdoc advisor. Masaya Koda, he was a postdoc when I arrived at Taiwan. Ibun Sena, he was also a postdoc, but now he's faculty in Vietnam. And Professor Dilip Ghosh and Professor Tilman Flynn, who is my current advisor. All right. Let me give an outline of my talk. So I first discuss about the overview and give a brief overview of what I'm talking today. Then I'll talk about matter-antimatter asymmetry, what it is and how it is created and what are the mechanisms for that. And I'll pick one of the mechanisms, which is called electric baryogenesis, with two Higgs doublet. So standard model plus one doublet, and try to explain how this matter-antimatter asymmetry is created. And then correspondingly, I would discuss some probes and some search modes for directly to search this type of setup. And if I have time, I'll just touch upon this cosmic inflation, which is in the same model, but it's mutually exclusive parameter space. And finally, I'll summarize my talk. All right. So I start with a well-known slide, and so this slide you have already shown. The subatomic world is pretty successfully described by standard model of particle physics, and this consists of fermions, mainly quarks and leptons. In fermion quark side, you have uptype and downtype quark, uptype plus 2/3 charge and downtime minus 1/3 charge, and you have charged lepton and neutrinos. And we have four fundamental forces, but today what I'll talk about mostly gravity decoupled much earlier and is not of our interest. So we'll talk about three forces. First, electromagnetic forces. Photon is the force carrier of it, and W and G boson, which are force carrier of weak nuclear force, and gluon, which is force carrier of strong nuclear force. And the last missing puzzle of the standard model was the Higgs boson, and it was discovered in 2012 at the Large Hadron Collider in proton-proton collision. So after its discovery in terms of particle content, standard model became complete. And this discovery was very important, partly because the Higgs boson, it gives mass to the massive particles in standard model via a mechanism called Higgs mechanism. And what it is, so you have this Higgs potential where phi is the Higgs field. And this potential develops a minima if lambda greater than 0 and mu square less than 0. So it has a minima around this value, and where V is the vacuum expectation value of this Higgs field. Once this Higgs field acquires this value, then electric symmetry is spontaneously broken, and the massive particles in a standard model like W, Z boson, and uptype and downtype quarks and charged electrons, they get masses, and Higgs boson itself get masses. So its discovery was pretty important, and after its discovery, its couplings to standard model particles such as W, Z boson, and quarks such as bottom quark, top quark, and tau leptons are measured. And within the error bar, we have found out that this Higgs boson that we discovered is more or less consistent with the standard model. So standard model is mostly emerging, or the confirmation of standard model is mostly emerging from a Large Hadron Collider with its already collected data. Now the question is it the ultimate picture, or do you need to go beyond the standard model particle physics, standard model feature? So in fact, we have to, because we have made observations over the years, and we do not have any clue how standard model can explain this type of observation. So what are they? First, neutrinos are massive. We already know that. And standard model with its particle content cannot explain how neutrinos are massive. Matter-antimatter asymmetry. In the universe, we mostly see matter, and we do not see that much antimatter. So, and we don't know how it's generated, and standard model cannot dynamically account for this matter-antimatter asymmetry of the universe. Then existence of dark matter, dark energy, it has been established over the years, and standard model has no explanation for them. Cosmic inflation, standard model indeed can explain it, but there are some problems. If I have time, I'll just touch upon. And then there are some theoretical motivation, for example, a hierarchy problem in standard model. So the observed Higgs boson mass, which is 120 giga electron volt. And we believe that, that there is some dynamical way of generating such a light Higgs boson mass. And for that, we need beyond the standard model physics. So these are some of the motivation and some of the observations that we have made over the years, for which we think that standard model is not a ultimate theory. We need a more complete theory to explain nature. All right, so today my focus would be mostly matter-antimatter asymmetry of the universe, and at the end of the talk, I'll just briefly touch upon cosmic inflation. So what is matter-antimatter asymmetry? When it is created? Okay, so let me start with this picture, and we have pretty good idea of what happened right after Big Bang, roughly around 10 to the minus 43 seconds. So around this energy scale, which is called Planck epoch, gravity, which is one of the fundamental forces in nature, which decoupled from other three fundamental forces. Okay, so this, at that time, universe temperature was 10 to the power 32 Kelvin, and energy scale of the universe was 10 to the power 19 giga electron volt. Right after that, when universe cooled a bit, when universe was roughly 10 to the power minus 35 second volt, a strong nuclear force decoupled from the other two forces. And right after that, universe expanded pretty rapidly. The temperature of the universe at the time was 10 to the 28 Kelvin, and the rapid expansion is so-called cosmic inflation. When universe cooled a bit more, when universe was roughly 10 to the minus 11 second volt, the energy scale was about TeV, 10 to the 3 GeV, and temperature was 10 to the minus 15 Kelvin. The electric symmetry was broken, and electromagnetic force and weak nuclear force got separated. And this is the energy scale that we can access today at collider experiments such as Large Hadron Collider. When universe cooled even more, around 10 to the minus 6 second, when the universe was minus 10 to the 6 second volt, then first protons and neutrons were formed. The temperature of the universe was 10 to the 12 Kelvin. When universe cooled more, and when universe age was roughly about few seconds, light elements such as deuterium, lithium, and helium, this was formed. Subsequently, when universe cooled more, and when universe was roughly 400,000 years old, first atoms were formed. And at this stage, all these photons trapped in this primordial cosmic plasma, they actually released, and we see today those photons traveling all across the universe towards us as a cosmic microwave background radiation. Okay. And then subsequently, galaxies were formed, and today we are at 13.8 billion years old. The universe is 13.8 billion years old, and temperature is 2.7 Kelvin. Something happened between right after cosmic inflation and before quark-hadron transition, phase transition scale, that all this antimatter from the universe is disappeared. We don't know how, but we have observations that we have seen in universe, that we know that all the antimatters will go. Okay, and this is so-called matter-antimatter asymmetry of the universe. All right, and let me explain a bit more. So what do I mean by matter? Matter in today's talk is basically electron, proton, neutron. It's called baryonic matter. So that's why I sometimes will interchangeably use baryon asymmetry of the universe. And antimatter is basically positron, anti-proton, and anti-neutron. So what do we know? We know that galaxies are made of matter. We do not see any antimatter galaxies. At least we have very strong limit that they don't exist. Universe could be globally symmetric in matter and antimatter. Okay? The part that we live in could be matter dominant. So there could be other parts of the universe which is beyond our observable universe that could be completely antimatter dominated. But then the observable universe size is 92 gigalight year, okay? And it's a pretty huge size. So to generate this kind of pocket of universe, local universe, you need to have a very complex dynamics, okay? And this complex dynamics is not easy to understand, or not an easy mechanism to create this kind of complex large pocket, where we have matter-dominated observable universe and antimatter-dominated other parts of the universe. Okay. Also, universe could start with matter-antimatter asymmetric way, so that could be the initial condition of the universe. But we have fairly good reasons to believe that cosmic inflation happened. So, if universe started during Big Bang with matter-antimatter asymmetry way, cosmic inflation will basically exponentially dilute this matter-antimatter asymmetry. So, any primordial asymmetry that if it had, cosmic inflation will basically wash away. Okay. So, what is the conventional belief? Conventional belief is that after cosmic inflation, cosmic reheating actually created matter-antimatter symmetric universe, and then universe evolved to a matter-dominated one dynamically via a process called baryogenesis. And this is the main topic of today's talk. And asymmetry, in most of the models, this asymmetry or this baryogenesis actually happened during or before Electroweak epoch. But there are some models where this matter-antimatter asymmetry can create during cosmic reheating or below Electroweak scale. But for most of the models, it's either at Electroweak scale or before Electroweak scale. All right. So how it is measured? So there are two ways to measure this matter-antimatter asymmetry. First, abundances of light elements. Light elements, which I mean is deuterium, lithium, and helium, and in how large quantity they are available in the observable universe. From that, one can actually infer what is the current baryon number density of the universe. And baryon number density I denote is NB. And NB is directly related to something called density parameter omega B. And omega B is given here, rho B divided by rho C, where rho B is basically energy density associated with baryon, and rho C is basically critical density of the universe, critical energy density of the universe. It has been found that this omega B, which is normalized with this reduced Hubble parameter, defined as H0. H0 is the Hubble parameter today, divided by 100 kilometer second inverse mega per second inverse. And if you normalize with that, the current measurement tells us that omega B H square equals to roughly 0.02 and plus minus some error bar. Okay, and the error bar is pretty stringent. Then there is another way of measuring this baryon asymmetry of the universe. What is the baryon number density at the current universe? This is cosmic microwave background anisotropy. So, which I basically abbreviate as CMB. The CMB, up to good approximation, can be treated as a perfect black body with a temperature T. And the observable in CMB is the temperature fluctuation that you probably have already heard of. And cosmological plasma, which is basically photon baryon fluid, can be treated as a perfect photon baryon fluid. So the speed of the photon baryon fluid will be exactly the same as sound speed. But due to presence of the baryon, something happens. It's something called rarefaction and compression. The speed of the sound speed in this photon baryon fluid basically gets reduced. Okay, so what it happens then? Odd peaks in the CMB temperature fluctuations basically enhances, and the even peaks basically get suppressed. What it is, so you can just look at this picture. So this is the temperature fluctuation in microkelvin square, and in terms of multiple moments. So you can see this is the first peak and this is the third peak. So these two peaks basically get enhanced if you have more and more baryons in the photon baryon fluid. Okay, so they basically reduce the presence of more baryons basically reduces the sound speed of the photon baryon fluid. So from that one can actually infer it. So let me show you a cartoon. Can you see my screen? Hello?
Yeah.
Okay, so let me just see this. So how this thing is actually dependent on it. So you can see in this axis, this basically the baryon number density. So if you increase it, so basically it reduces because of the reduction of the sound speed. And if you you can see that the second peak, third peak and the first peak basically gets larger if you increase this number. Okay? But the second peak it basically gets reduced, and you can see the relative size. This is larger than the second peak. So from this relative size, this odd even peak disparity, one can actually infer the number of baryon number density. And Planck collaboration actually provided this number, and you can see this number is this one.
So I have a question.
Yeah,
So
please.
just assume that there is no baryon. So then how this graph would look like, or let's say it's a single fluid of radiation. Only there is photon. So then uh, there will be peaks, or there will be no such peaks.
If you just have photons,
Yeah.
if you have no baryons,
Yeah.
it will basically all the photons will travel all over the universe. You will see no field. So no basically temperature fluctuations.
So
Because the universe is expanding, so all this photon will be basically dispersed in as the size of the universe enhances. So this is the sound speed of this photon baryon fluid. From that we can basically measure the temperature fluctuation.
So
So if you do not have, okay, yeah, please go ahead.
so then in this plane you'd get a flat line, or so how this graph
You
would
will
look
not
like?
get you will not get any temperature fluctuation. So if there is no so you cannot measure anything. So the photon will be dispersed to all directions of the universe, and you will not see this temperature fluctuation curve.
Okay.
So this is something called baryonic acoustic oscillation.
Yeah.
So if you measure the baryonic acoustic oscillation, from that you can actually measure it. But if you do, so okay, so the question was your question, if you do not have baryon,
Yeah.
or if you are talking about you can have other material like dark matter, right?
No, I'm just saying just
Nothing, just photon.
just photons. So photon has some pressure, so there would be some pressure waves for the photon.
It will just expand. So there is no gravity to pull them together.
Okay.
So it will just expand as your universe expands. Expands.
Okay. You go on.
So so both the observations basically point towards the same number. You can see this number. So you can see they are roughly same with okay, there is some discrepancy and there is some mismatch between these two numbers, some 2 point some sigma deviation, but I'm not going to explain today that. But they essentially points out to same number. So from that, one can actually express this quantity in a convenient way, which is so-called baryon to entropy ratio. And this is how you actually express. So you basically expand this rho b, omega b in terms of rho b divided by rho c and h squared. And rho b is basically mass of the proton times number density of baryon, and mass of the electron times number density of electron, and then divide this quantity by critical density. And then you normalize that quantity by dividing the entropy density. And entropy density depends on this temperature, and from that you can actually get this number, which is convenient. I said it's a convenient way to express it because this quantity is conserved during expansion of the universe. How? Because NV actually scales as 1 by a cube minus a cube, which is a to the power minus 3. A is scale factor, and AS also expands as a to the power minus 3. So it basically cancels in the ratio. So when the universe expands, this number basically remains constant. And so that's why people typically express in this way. And this is the so-called magic number. And if you have any model, you want to explain this number, how this number one can actually account this number. And in most of the models, we basically try to express in this way that the baryon asymmetry that we in the universe we have is 8.6 times roughly 10 to the minus 11. All right. What are the conditions for baryogenesis? It has been laid out by Sakharov long back in 1967. So you start with a universe which is a baryon symmetric universe, and delta B, basically change in baryon number is 0. And then you evolve to a baryon asymmetric universe where delta B is not equals to 0. You need to have C and CP violation. And if C and CP are conserved, there will be no baryon asymmetry. And departure from thermal equilibrium. So if you have thermal equilibrium, if there is any mechanism that creates some baryon asymmetry, the thermal equilibrium will basically send the asymmetry back to in a symmetric way, in a baryon matter antimatter symmetric scenario. And there are plenty of models, or plenty of alternatives to account for this baryon asymmetry of the universe, satisfying all these three conditions. Electric baryogenesis, guard baryogenesis, leptogenesis. I picked up some of the mechanisms, and each with their own advantages and disadvantages. Actually, spontaneous baryogenesis is something called where you have CPD invariance, CPD breaking of CPD, but it restores at late time. Okay, but today I mostly focus on electric baryogenesis. What is electric baryogenesis? So it has been found that all three Sakharov's conditions can be met at electric phase transition. And since it is connected to electric phase transition, and we know that current energy scale or current accessible energy scale at collider experiment is around electric scale, so one can easily probe this type of physics and test this type of scenario. So it's connected to Higgs physics, and there are exquisite probes for collider experiment. So that's why most of the people get really excited about electric baryogenesis, and which is why I also get excited. And today I'll focus on this particular mechanism. Okay. So what is electric baryogenesis, and what are the conditions that you require for electric baryogenesis? So you need to have a hot radiation-dominated RND universe before electric baryogenesis. And then at that stage, electric symmetry is unbroken, so it's called symmetric phase. And then universe cools down below electric scale, which is roughly the temperature of 100 GeV. And once the temperature of the universe goes below this energy scale, then Higgs field settles to a vacuum, and that vacuum basically breaks electric symmetry into U1 electromagnetic. And during this phase transition, bubbles actually form bubble of broken phase. So you have a symmetric. I'll show you in the next slide in a diagrammatic way. So you basically have a nucleation of bubble of broken phase within the surrounding symmetric phase. And inside that bubble, you basically have baryon asymmetry. And it happens, all of these things happen actually during electric phase transition. And together, this process is called electric baryogenesis. Okay, so how it's created, let me expand a bit more. So you can see this picture. So this kind of blob is essentially denoted as, inside the blob is denoted as broken phase, where the vacuum expectation value of the field is non-zero. And you have symmetric phase outside, where the vacuum expectation value is 0. And this is the blue thick line is called bubble wall. So inside bubble of broken phase, and this is the symmetric phase, and the electric symmetry is not broken. And L are basically left-handed fermion and right-handed fermion. So if you have CP and C violation, basically charge conjugation parity and charge conjugation violation in the underlying theory, then you can actually generate a left-handed number density compared to the right-handed number density. So you have excess left-handed number, which is via, if you have CP violation, so via this process. So this, all these left-handed and right-handed fermions basically collide with this wall of this broken phase. And if you have underlying CP and CP violation, you generate basically left-handed number. Okay. And then electrics Halleran process is a bit complicated to explain in this type of talk. So it's a kind of process which basically generates from left-handed number density or left-handed asymmetry, generates a baryon asymmetry. So electric Halleran in the symmetric phase basically generates a baryon asymmetry. But then electric Halleran process, after generating it, actually tries to wash it out, or basically tries to destroy it. What happens? So this electric Halleran process inside this bubble is basically quenched. So that means it's basically very suppressed. And the bubble grows with velocity of sound. It depends on your underlying model. And once it basically grows, this broken phase bubble grows. It basically sweeps inside this broken phase bubble some of this baryon asymmetry that is created in the symmetric phase. And that's how inside the broken phase you have some baryon asymmetry generated. So this is how basically in electric baryogenesis you generate baryon asymmetry. All right. Do you have any question up to here? All right. So I go to the next slide. Okay. Standard model is electric theory. So can it generate or can it account for the observed matter-antimatter asymmetry? In fact, standard model has baryon number violation inbuilt in it due to triangle anomaly or chiral anomaly, which is tiny at 0 temperature but could be unsupported at finite temperature. And since we are doing talking about finite temperature physics for electric baryogenesis, it could be unsupported at finite temperature. So it has been discussed in this last 2 papers. And weak interaction violates C, charge conjugation maximally, and it has CP violation inbuilt in standard model, all of you know, via CK matrix. And however, it has been found that the amount of CP violation in the standard model is too tiny, and too tiny to account for the observed baryon asymmetry of the universe. And the departure of thermal equilibrium, typically in electric baryogenesis, it has been satisfied by strongly first order electric phase transition. And Higgs boson mass is too heavy to account for this strongly first order phase transition. The mass is 125 GeV, and from lattice calculation, it has been found that if Higgs boson mass was below 80 GeV, roughly around 80 GeV, then one could have actually strongly first order phase transition in standard model. But since we discovered the Higgs boson mass is around 125 gigaelectron, so we know that strongly first order electric phase transition is not possible in standard model. All right. So what happens if we add one doublet and just one doublet to the standard model? And that is what so-called general intuitive doublet model. It has been discussed in literature that it can do it. It can account for the observed baryon asymmetry of the universe. For example, in this 2 paper, it has been discussed that coupling rho tt. So these are some Yukawa coupling. I will define what they are. Just remember this number. If rho tt is in this range, and rho tc is greater than 0.5 with maximal phase, that means their value is completely imaginary or almost imaginary. And if rho bb is something called extra bottom Yukawa, I will discuss what they are. If the value is greater than this value, then it has been shown that it can provide additional source of CP violation, and which would be enough to account of the baryon asymmetry of the universe. So one of the shortcomings of the standard model is satisfied here. So 2 small CP violation is accounted here, and additional Higgs bosons. So you have additional parameters in this Higgs doublet model, which can, in principle, induce a strongly first order phase transition, and it has been showed that due to presence of this additional Higgs boson, one actually has strongly first order phase transition. So in fact, in general Higgs doublet model, one can successfully account for this observed baryon asymmetry of the universe. Of course, there are some uncertainties. If I have time and if you are interested, I can discuss. But bottom line is, general Higgs doublet model can account for the observed baryon asymmetry of the universe. And also remember this coupling values and this mass range, which would be useful for future in future slides. All right. So electric baryogenesis with 2 doublets. Let me start with this well-known potential. All of you know this thing. And today I talk about CP conserving Higgs sector with no discrete symmetry. So I have all the 7 quadratic couplings and 3 dimensional parameters. All right, so it has been discussed by, there could be other papers before, but mostly discussed in Davidson and Haber, and you can also look at this paper as well. And of course, some of you also have probably written many papers on this Higgs doublet model. And in the Higgs basis, so I today talk about Higgs basis because of course there is some finite temperature dependence, but since I do not have any discrete symmetry, I cannot distinguish between phi and phi prime. So I can define tangent beta, which is ratio between the wave between phi and phi prime. But there would be no physical meaning for tangent beta because we do not have any symmetry to distinguish which one is V1 and which one is V2. So I go to Higgs basis, which is called so-called physical basis. And once the symmetry, electric symmetry is broken, we have H, which is 125 gigaelectron of Higgs boson, capital H, which is CP even Higgs boson, and A is CP odd, and H plus minus, which is charge Higgs. And cosine gamma is basically mixing angle between these 2 CP even states, small h and capital H. And current data basically constrain this thing to roughly 0.2 to 0.1. Depends on the Yukawa couplings and things, but roughly this values are still allowed. And cosine gamma is equals to 0 or tends to 0 is basically so-called alignment limit. All right. The UCA sector, since we do not have any discrete symmetry, both the doublets coupled with up and down type fermions. After you diagonalize the fermion mass matrix, you have two different UCA sets. One is lambda f connected to the mass matrix and given by this expression, and the other one is rho f. Rho f is in general diagonal complex, and lambda f is real and diagonal. So you can see this thing. Okay? You can see for so this is the up type UCA matrix down type, and this is the left hand side. Okay? And the third element, or basically 3 element, is essentially the largest, as you all know, because this is connected to the top curve mass, and this is connected to the bottom curve mass, and this is connected to the top mass.
So, can I ask one question?
Yes.
So, in the previous slide, the gamma, the cosine gamma, what you just showed. So, this
Yes.
gamma is the angle between the CP even sector. I mean, rotation angle of the CP even sector.
Right. Small h and capital H.
Okay. So, so this value has to be small. Is having some constraints, experimental constraints, or is it chosen?
No, it's coming from some experimental constant in the setup. Okay, it depends on slightly on the coupling assumptions and things, but it's mostly coming from the experimental constant. I'll show you from where it is coming.
Okay. Okay.
And okay, so this is so we basically neglected. So we assume CP conservation in Higgs sector, but at UCA sector we'll assume CP non-conservation. So at one loop level, all these couplings would be complex. So all this small h, capital H, and capital A, they will all mix. All this neutral 3 Higgs boson will mix. But this that angle would be very, very small because it's basically loop surface. So we ignored that mixing angle. So essentially, small h and capital H are practically CP even state, and this is practically CP odd state.
So, at a starting point, we are starting with the CP conserving electroweak sector, right?
At tree level, yes, here.
Yes, tree level.
In the Higgs sector.
Yes. Okay. Thanks.
And in the UCA, okay, so that is precisely the next point. So in the UCA sector, you have basically 3x3 matrices, and for up type, down type, and left hand sector, and all of them could be in principle complex, and all of them are independent. So you can allow data to constrain them from flavor physics collider experiments. So and there are some of the elements are already constrained pretty strongly. But roughly what we do, we assume this type of structure that in the row matrix, we roughly have the same structure as the standard model like UCA sector, which is this lambda UCA sector. So the 3 elements are roughly assumed to be pretty large. So that means rho TT, rho BB, and rho tau tau could be large, although we turned off rho tau tau, and we assumed rho TT, rho TC, and rho BB to be non-zero. And for all practical purposes, we just turn them off if we do not need them. But this is just effective theory. You can ask you can construct a model, but we just treat them as effective theory and just switch this coupling off by hand. No symmetry, nothing. All right. And so our focus is rho TT, rho TC, and rho BB. And I will show that all these 3 couplings could be still large. And you have sub TeV heavy Higgs boson, roughly around 200 to 600 GeV. And if you combine these 2 things, you have electric baryogenesis. And if you combine these 2 things, I will show in the next slide that you also have discovery as well, larger than collider or some flavor physics machine such as Bell or LHCb. And this is the most important 4 lines of my talk. Look at the UCA couplings of the heavy Higgs boson. So this combination is what we measure at experiment. So this is 125 gigaelectron Higgs. This is capital H. This is capital A, and this is charge H. And I told that cosine gamma is roughly about 0.1 to 0.2. That means sine gamma is practically 1. So for 125 gigaelectron Higgs, it mostly couples with lambda Ij. Okay, and that means it's basically coupled with the standard model type of UCA coupling. But for heavy Higgs boson, for example, capital H, you can see the lambda is coupled with cosine gamma, but rho is coupled with sine gamma. That means this part is suppressed, and rho is basically enhanced due to is proportional to cosine gamma. So discovery of the Higgs or this phenomenology of this Higgs is practically dependent on rho Ij. And same is also true for A, and same is also true for H bar or charge Higgs. And B is basically CK matrix. Okay? And you can have a look at these couplings and try to understand that what are the couplings that I will use. You can easily see that rho TT, rho TC, and rho BB are the couplings, and all of them discovery will be possible with this coupling. How? And so in the next slides, next few slides, probes at collider experiment. So first I'll discuss our topic called electric baryogenesis and correspondingly their probes. That is this rho TT and rho TC first, and then I'll talk about rho BB. Okay. So first, I start with in the search. For example, Higgs boson couplings are measured, and typically it's measured as a ratio between the observed production rate divided by the standard model rate, or observed decay rate divided by the standard model rate. And the typical parameter, if you read this paper, is kappa t is roughly 1.01. So it's basically ratio between the standard model observed cross section divided by standard model cross section, or observed decay rate.
Tanmoy,
Yes.
so
Yes.
basically then you have explicit CP violation in this model, right?
Explicit CP violation in the ECO sector, yes.
So if you have explicit CP violation, then will you have a pseudo scalar?
You have a CP or pseudo scalar, yes.
But if you have explicit CP violation, then all the Higgses should be mixed, right? Then you have a phi 1, phi 2, phi 3.
Okay, so at tree level we do not have CP violation in the Higgs sector.
So in the potential, the parameters are all CP conserving.
All
so there is so in the potential there is a CP conserving potential, and there is no mixing between the scalar and pseudo scalar.
No mixing. At one loop they will be generated, but they are.
So, but if you have Yukawa coupling, will that lead to mixing at one loop level?
Yeah, exactly. That we checked is very, very small. We can practically assume them as a CP even or CP offset. It's practically negligible, that mixing angle.
Even at the third generation sector?
Even at the third generation sector.
No.
It's very, 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 very small. This one is a tree level coupling. So you have some imaginary part here, but that will be pretty small due to one loop level separation. And that is essentially what we do in this Kohlberg-Weinmann potential.
Yes,
you have
yes, yes.
one loop character potential, temperature driven potential is minimized, and that part is basically.
Okay.
So there are two. Okay, so essentially you have to calculate the Yarskov invariance. So even if I say that my row couplings are complex, that doesn't mean the theory has to be violation. So you have to basically construct a Yarskov invariant to basically account for this observed to account for the CP violating source term for baryogenesis. And one of the way of generate, there are a couple of ways. You can actually generate the CP violation from the Higgs sector. Basically, you can turn on either eta 5, eta 6, or eta 7 to be complex.
Yes.
Or you can have or also mu1 2 can be also complex, but it is connected by this stationary condition. You can replace them by some couplings, quadratic couplings. But also in the ECO sector, you can have a CP violation. But that doesn't mean you have CP violation in the theory. So you have to actually construct a CP violating source term or Yarskov invariant to see whether you have net CP violation in the theory. And the net CP violation, if you calculate in the theory, are proportionally imaginary part of these couplings. And that's why we say that if you have imaginary this coupling, you have CP violation that is accounted for baryogenesis. I have those calculation in the backup slide if you're interested in so.
Okay, thank you.
Right, so you have this measurement of the top ECO coupling at LHC, and if you apply and your ECO coupling I showed in the previous slide. So if you use this coupling structure and assume that all other couplings are 0, basically, you have constraint on this real part of rho TP and imaginary part of rho TP. You can see practically the imaginary part is unconstrained, which is white region is unconstrained, and the shaded region are basically excluded by this measurement from Atlas and CM. And this is with full run to data. And I basically superimpose this figure, so that doesn't mean the CMS stops here. Actually, CMS goes also in the left side, and here also in the left side. Okay. And you can see the reason why imaginary part is basically very less constrained. You can see from this expression. Lambda is real, so if you can break this row into real and imaginary part, so the real part will basically interfere with each other, and imaginary part will be added in quadrature. So that's why it's basically less constrained. All right. Also, P2CH, the top quark decay to CHAM and Higgs boson is also measured. This is a favor violating coupling, and this favor violating decay, and this favor violating decay is measured. Atlas and CMS they do not observe it, but they set a very stringent upper limit on this branching ratio of T2 CHAM and Higgs boson. And this decay is directly proportional to rho Tc, and it's also dependent on cosine gamma. So you can see roughly what value you need for baryogenesis, roughly 0.5. So around this value. So if I just draw a line, it hits roughly around 0.15 or so. And so you can see that this value is roughly excluded, or you already have some constraint. So if you go 0.2, so you can already see that parameters for baryogenesis is already excluded. And I have not discussed much about dependence of baryogenesis on this cosine gamma. Roughly, I can tell you that for baryon asymmetry, you need cosine gamma to be at least or roughly around 0.1, or at least greater than 0.1. If it is smaller than 0.1, then baryon asymmetry, generation of baryon asymmetry probably is not possible. Although we have not done any calculation, this is our understanding, and it's ongoing work. We still do not have any answer for that, but roughly 0.1 is what we think is a reasonable number, and if it is below, then we cannot actually explain the baryon. All right. Then there are other indirect measurements. For example, BS mixing. This is by far one of the strongest constraints, and this is what we discussed in a paper with Professor Bose and Professor Howe. And in this paper, we showed that actually BS mixing. Also, there are other papers, so we also discussed this thing as well. So we saw that so this type of box diagram is possible, including charge higgs and bottom and top loop. And this type of loop actually can induce very strong constraint on magnitude on rho Tt. So you can see in the previous slide, I showed what is the value required for baryogenesis. So here, so roughly 1 is also allowed. So part of the parameter space is already excluded. So if you see any deviation in future, you can see, okay, it might be maybe coming from electric baryogenesis. So roughly you can see that quite a bit of larger side of the value of the coupling is already excluded. And for baryogenesis, roughly around 700 GeV is upper limit. So if you have heavier Higgs boson, strongly first order phase transition is not possible. So around 700 GeV is kind of ultimate limit for baryogenesis. All right. For example, direct searches. Direct searches are also possible. Rho Tt is the favor conserving, and rho Tc is the favor violating. For favor conserving top alpha, rho Tt, there are already existing searches. For example, all of you know this thing: glue fusion to heavy Higgs boson production, and then it decays to Tt bar. Although it has some problem with interference with the standard model Tt bar background, because the initial state and final state are same. So it will have some quantum interference, but recent Atlas and CMS study found to be sensitive, and they already constrain roughly around 1 magnitude or value rho T of the order of 1 is already excluded for 400 GeV or so mass range. You can also have 4 top search, Tt bar A production, and then H and A can decay to Tt bar, and that can also be used as a search program. And we have also discussed this thing. We do not discuss, but essentially they can be used for search. And then this process, it is actually gluon fusion to A production, and then A and H can decay to top and CHAM top if your rho Tc coupling is non-vanishing. So the production is dependent on rho Tt, and the decay is dependent on rho Tc. And it could be also discovered, but there are some issues on mass resolution for top quark and jet. Due to that, some of members of CMS in my previous institute think that this process could be probably not sensitive for LHC. Then we propose some search modes because these processes can also go, but then we additionally propose some search modes. In this side, you can see there's some neutral Higgs production. The Feynman diagrams are given here. So you have CHAM glue fusion to top quark and a pseudo solar production or top quark heavy Higgs production. And depending on what you couple, so this production is dependent on rho Tc. So all these productions are dependent on rho Tc for neutral as well as heavy charge Higgs production. But the decay depends on what you want. So if you have rho Tc coupling non-zero, then A and H can decay to T and CHAM cup. And if rho TT coupling is non-zero, then it can decay to TT bar. And we found that this could be very clean probe because it's same sign probe, same sign dielectron signature. It's pretty clean probe for LHC. Triple drop is also may require high luminosity LHC, but it's also very clean because if you decay all of them, all three of them in same electronically, so you have 3 electron 3 behaves, also pretty clean process. And this is top assisted dihist, and we discussed that this can be also discovered, but it requires high luminosity LHC or roughly around 450 GeV mass. If it is beyond that, one may not have discovery, but may have some evidence. And this is important because this gives some insight about how electric symmetry is broken, because it connected to the Higgs potential, capital H to HH, probes some parameter space of the Higgs potential. And you also have this TA to A can decay to Z boson and H. And this process is important because it has been shown in this paper that capital A to Z boson H decay is favored by strongly fast order phase transition. As you remember, in the previous slides, I said that strongly fast order phase transition is necessary condition for electric baryogenesis. And we showed that, around 300, 400 GeV one can actually discover this process. And then we have also discussed these charge heat processes. And all of them could be discovered, but some of them, for example, these two may require high luminosity LHC. Or not this one. This one can be constrained with the current run to data. And these processes are being searched at both Atlas and CMS collaboration. Atlas collaboration at Barcelona University, they're searching the past 2 processes, and they have asked for model file for these 2. And CMS collaboration are searching for this and this process. CMS collaboration in my previous institute, National Taiwan University, and in collaboration with, I think, Peking University, if I remember correctly. And for charge Higgs, there are no such proposals so far from Atlas, although there are some proposals from CMS, and they are actually searching. It's also my previous university, National Taiwan University. They are searching this first process. And if you are interested, you can have a look at this wiki page where you have this neutral Higgs production processes and model files. If you're interested, you can simulate this thing, cross-check, and if you are interested, you can also see whether these are reasonable such processes. So far, I did not have any time to create any wiki page for charge Higgs, but I'm trying, but I'm occupied with some other things and I couldn't have time to click on. All right. So give an idea about how the particle level cross-section looks like. Okay. So in the previous slide, when I said the discovery, it means all detected effects and things are included, like hadronization detected effects are included. But here I'm just roughly giving you a sense of cross-section, how large this cross-section could be. So if you look at the TA and TH production in this Feynman diagram, it can hit up to picoband level. Then branching ratio of A and H to TT bar or top charm is roughly about 50% or so. So you can see how much at particle level the cross-section could be is quite large. And since the background cross-sections are pretty much controllable because of the finite state topology, so one can actually have a discovery at LHC. All right.
Is it possible to get similar kind of coupling the leptonic sector?
You mean the rho tau mu?
Yes.
Yes, you can. Today I don't have slides for it. In fact, we have looked at some leptonic decays, for example, B2 mu nu and B2 tau mu. It has this tau to mu coupling, and that is not connected with baryogenesis directly. Although rho tau mu could be connected with baryogenesis, but there are strong limits for tau to mu gamma. So that basically kills this thing. But today I do not have the slide because partly I did not directly work on that rho tau mu except one project, and it's mostly constrained, so I did not include that flavor physics type of thing to it. I might have in the backup slide, but I will probably look at it.
Okay.
All right. And so you can look at this Atlas and CMS as some searches, and they already kind of constrain this type of parameter space. For example, this same sign top that I discussed, 2 same sign dilepton, 3 jets with 2 detect. And these searches are not actually meant for the same sign dilepton probe, but the finite state topology are similar, and I found that it can actually constrain. And so we used it, and we found that it can probe some parameter space. Even rho TC5 is 0.5 is required for baryogenesis. You can look at for quite a large part of private space is already excluded. And for future
So
discovery,
you are saying that suppose you look at this 500 GeV or 400 GeV Higgs, and if you have a rho tau mu kind of a coupling, so can Higgs be looked into that mode also?
you mean
Higgs
capital
be
H to tau mu? Capital H
Yes.
to tau. Yeah, in fact, George actually searched in a couple of papers with his collaborators.
Okay.
And they are searched already, and they looked at this thing in detail. Yeah, there are search.
Okay.
And yes, you have some projections with. So we basically these searches from Atlas and CMS are not direct searches. So we kind of propose some proper search, and you see these projection limits with defined luminosity. And 5 sigma is basically this red line, and their exclusion limit 2 sigma is for defined luminosities are plotted in blue
So
lines.
how this limit will change? Suppose if I look at same process, Cg going to Ta/Th, and then H decaying into, instead of this tau C, if it decays into tau mu. So how this bounds will change?
Oh, then it depends on two couplings, right? Rho Tc and
Yes,
rho
product of
tau
two
mu.
couplings. Yes, product of two rho Tc and rho tau mu.
I think it's not that strong if you just kind of tune what you need, either rho Tc tuning or rho tau mu tuning. But roughly, I think if I remember correctly, it should be around 10 to the power minus 3 level, if I remember correctly. I have to check exactly because I have not been on the paper and I have not searched it, but I can send you the link. But it's roughly about 10 to the power minus 3, the product of the coupling around this answer. Okay, so this is in the previous slide, which was a flagship experiment for flagship search mode for neutral Higgs. We also have a flagship search mode for charge Higgs, and this process is missed. And with Professor Ghosh and Professor Howe, we showed that this process could be actually enhanced. You can look at the production process is proportional to VTV. You can look at the Lagrangian I showed in the previous slide. And also you can look at this decay, which is H plus decay to top and bottom. That is also proportional to VTV. So the whole entire process is proportional to VTV square, and VTV is roughly 1. So this process is CKM enhanced. Like there is already existing search processes at LHC, which is this bottom gluon fusion and H plus production, and then H plus can decay to top quark and bottom quark. Okay? So these are standard search. But for our case, it's very interesting because it's enhanced by PDF of Chamkor. Okay? And we have shown that if you have mass range from 300 to 500 GeV, 5 sigma discovery is possible with 600 femtoran inverse rate. Although there are some problems of background normalization, because you know that TTR background is huge, and the background normalization could be some issue. But our discovery and discovery process is actually generated with rho TC 0.4 and rho TT 0.6. These are not the upper limit. Upper limit is actually much higher, close to 1. So if you saturate this upper limit, then your signal to background ratio becomes much larger, and your background normalization could be much improved. So these are basically searched by CMS collaboration. I can give you exactly how in actual analysis in Atlas and CMS how it looks like maybe in future in coming months. All right, and so we finally discussed how, at least for the rho TC driven electric baryogenesis, how things would look like. And so these red lines are basically charm group to gauge production, and then H plus can decay to small h to W plus, and this decay is dependent on cosine gamma. And we showed that combined with this TA is the same sign of production that I showed in previous slide. If you combine with this thing, you can actually exclude the entire electric baryogenesis induced by rho TC, and you can see this line required for baryogenesis. So baryogenesis is required in this region. So you have to have cosine gamma larger than 1 and cosine and rho TC larger than 0.5. So in this box, basically you need. And you can see the current data, which is the shaded region, for 350 GeV is almost excludes the parameter space. For 500 GeV, it's still there, but future probes can actually exclude the entire parameter space. Okay. What about bottom echo? So far, I have not discussed anything about bottom echo. If you go here, so And so far, I have not discussed anything about how to probe the CP validating phase, which is important for baryogenesis. In fact, it has been shown that delta ACP, which is this CP asymmetry of B to S photon, inclusive B to S photon measurement, charge and neutral, and that asymmetry of CP asymmetry can probe the parameter space for imaginary OBB quite stringent. You can see by this shaded region. It's actually excluding quite a lot of parameter space. Here we assume rho T to be 0.5, and I'm showing for imaginary rho BB. One can actually do the same and plot for imaginary rho TT, assuming some rho BB coupling.
Tanmoy, you have 4 more minutes.
Yeah, so I just need 2-3 more minutes. Okay? You can see these couplings are actually dependent on this is the Wilson coefficient coming from these heavy charges, and you can see how the dependence is. Okay? And in future probe, this is required for electroweak baryogenesis and 0.058, and you can see delta ACP can actually probe the entire parameter space if you have parameter values are in this range. All right. And also for imaginary rho BB, there are search from Atlas and CMS, for example, Higgs to BB bar coupling measurement, and you can see it is also not strong, and ILC future projection is also not strong. So the white region is still allowed, and in the future, the blue lines are from ILC, and you can still see the there are some parameter space left for rho BB electric baryogenesis from this indirect measurement. Okay. And EDM, which is by far one of the most stringent constraints, unless if you switch on some other coupling, electron EDM actually exclude all the parameter space for at least rho TT and rho BB driven electric baryogenesis. However, there are some cancellation mechanisms. For example, if you turn on imaginary rho E, very tiny amount, which doesn't have any impact on any direct and indirect search except for the EDM. And if you turn on this coupling, we have showed that there are parameter space and imaginary rho BB is as large as 0.15 is still allowed.
So this cancellation is 1 loop level or 2 loop level?
This is 2 loop Bargy diagram, yes, here.
Oh, okay.
And there are some direct searches as well. So one can actually, by 2030, one can actually exclude or discover the electric baryogenesis driven by this extra bottom Yucca rho BB conclusive. I mean, one can say whether this is the mechanism or this is the coupling that is in that has generated the variance of the universe. So it's basically a testable scenario. All right. Cosmic inflation. I don't think I have time to discuss this thing. I can discuss offline. There are parameter space for cosmic inflation as well, but it's not mutually inclusive parameter space. Cosmic inflation parameter space is mutually exclusive to baryogenesis. So far, we are trying to incorporate both, but we are unsuccessful. Electric baryogenesis and cosmic inflation in the same model. Numerically, what we have found is not possible. All right, so I do not have anything to say that, I mean, do not have time. I roughly say that for cosmic inflation, we found that it requires nearly degenerate mass spectrum for heavy Higgs boson. So if we see in future experiments nearly degenerate heavy Higgs boson, it might indicate that cosmic inflation is induced by Higgs doublet model type of scenario. All right, so I summarize. So today I talked about standard model plus one extra doublet, general Higgs doublet model for electric baryogenesis, and there are couplings, for example, rho TT, rho BB, which could be complex and they can induce electric baryogenesis and account for the observed baryon asymmetry of the universe. There are novel signatures I discussed at LHC and future experiments such as ILC and FCC EE, or ongoing experiments such as BIL2 actually offers sensitive and complementary probes. Cosmic inflation, it's possible in this model, but mutually exclusive parameter space, and it requires or it points towards nearly degenerate mass spectrum. And if discovery happens of this new Higgs boson, depending on what is the mass range and things, one may have some understanding about how matter-antimatter asymmetry of the universe is generated, or may have some idea about what is the mechanism behind cosmic inflation. All right, thank you.
Thank you, Tanmoy, for excellent talk. So now the session is open for questions, comments, discussions.
So, so I have a couple of questions. So,
Yeah, please.
yeah. So, first one is that you talked about the Sakharov conditions. So, and the third condition was departure from thermal equilibrium. So, in the, let's say, for gut baryogenesis, or when we talk about departure from thermal equilibrium, it meant that some mother particle number density goes out of equilibrium. So then only the baryogenesis can happen. So when you talk about this electric baryogenesis, so what do you mean by the thermal equilibrium, and what do you mean by the departure from thermal equilibrium? So how this is achieved, I couldn't get that.
So here, what it happens? Okay, so I didn't go in details. What it happens basically, your Spalaron process in the broken phase, the rate of the Spalaron process. Okay, so this is quenched. So the rate of the Spalaron process in the broken phase has to be smaller than the Hubble expansion rate. That is the condition. Okay. It doesn't. So far, it doesn't. So this is the condition for freezer condition, right?
Yeah.
So it has to be the rate has to be lower than the Hubble rate at that time, at that epoch. All right. So that condition actually doesn't talk about strongly fast order phase transition and departure of thermal equilibrium.
So that means the particles in the bath, let's say the Higgs and other BSM particles, are all in sharing the same temperature as of the photons.
That is the symmetric phase. Yes.
So.
So your baryon number, baryon number asymmetry is generated in the symmetric phase. Universe is expanding, and your bubble of the broken phase is also expanding. Okay. And expansion of universe is that speed is different depending on at which epoch you look at, but the bubble is expanding with the velocity of sound wave, which is denoted roughly VW in our case is roughly about 0.4 or so. And that is so your bubble is expanding, and so this expanding bubble actually sweeps some of the generated baryon asymmetry that is in the symmetric phase inside this bubble. Okay.
So the point is that you have a distribution of these 5 particles. So in a particular time, there is they do not acquire some wave, and some of them has acquired the wave. So, and there is some disparity. So that's why the bubble is formed.
Yes, there is thermal tunnel. Yes.
Okay. So okay. Then and my second question is that.
No, I think I still have not explained to you how the baryon number is generated. So it just went inside. Okay.
Okay.
So now your Spalaron rate is quenched inside this broken bubble. Okay. So that means your rate of the in the broken phase, the rate of the Spalaron is lower than your Hubble expansion rate.
Okay.
So it's frozen out.
So
and it's found if you just do a bit of calculation, it's found out that condition required for this, if you satisfy this condition, depending on what is the Spalaron energy in the Yang-Mills theory, here the Yang-Mills theory is SU2 cross U1. So if you calculate a little bit, you find that Vc by Tc, which is critical wave by critical temperature, that has to be greater than 1, or roughly of the order of 1.
Oh.
Coincidentally, in electroweak phase transition, if you have Vc by Tc greater than 1, that is called strongly fast order phase transition.
Okay.
So that's why people talk in electric baryogenesis. If you have strongly fast order phase transition, that basically induces the departure of thermal equilibrium. So it's clear?
Okay. So I have to read these things. So for the timing, it's okay. So
okay.
I am going to my next question. So the next question is, so let's forget about the collider signatures and all the direct search, all the stuff. So if you concentrate only on that cosmological number, that is n beta is something order 10 to the minus 10. So now if you look at in your this 2 Higgs doublet model, so which are the parameters you can constrain solely from the cosmology? But if I forget about
cosmology, which experiment?
So let's say you have only knew about the number that baryon asymmetries of the order of 10 to the minus 10. Now you say that the baryogenesis has occurred through this electric baryogenesis. So yeah.
So if you do not have any experiment, anything doing, every single coupling can account for it.
Oh, that means
every single coupling that has
collider will give you a much stronger constraint.
Yeah, no, he's saying that if you remove, he's saying that if you remove all the collider constraints and think all the experiments, so what would happen? So okay, so there are a couple of things. The question you have asked, in principle, all these couplings can actually generate the same number, this whatever number I showed you. But then there are some preferential coupling, okay, in generating baryon numbers. For example, here you see these three couplings I have talked about. But if I go here, okay, sorry, here, in principle, all these couplings can generate. But depending on these couplings, there are interactions between the bubble wall. So you see here, the asymmetry is generated if you have Cp and C violation in the plasma. Okay? I have not showed you. Let me show you in the slide. It's too complicated to even in a seminar, in a technical seminar, it's even more complicated to even complicated. So there are several rates in the plasma. So you have some diffusion equation.
Okay.
And some of the diffusion equation directly depends on this eco couplings, okay? And some of them are actually enhanced. So it is what one has found. So top ECOs are typically very robust in generating the baryon asymmetry. So that's a rho TT. If you remember correctly, rho TT value is pretty large range is possible, which is not the case for other couplings. Here you see 10 to the power minus 22 is beyond the limit for maybe your if some experiment happens even in your grandkids time, that cannot also probe this 10 to the minus 2. It's pretty small number. And then there are some uncertainties. Okay, so there are of course some preferential couplings that can actually induce baryon number asymmetry without any collider constraints and forgetting about all collider constraints. Mainly this, so which is why we chosen these three couplings for baryon asymmetry. But yeah, there are many models which can account for baryon asymmetry of universe. But for Twiggs doublet model, mostly these three couplings are easy. You have MSSM type of baryogenesis where you have G2 symmetry. Today I did not cite all these papers, and there are huge literature for that. And already probably some existing members of ICS already have probably worked on those type of. I'm sure we have worked on MSSM type of baryogenesis and some minimum flavor violation type of scenario. There are CP violation is also possible in this type of scenario. But if you just look at the Higgs sector of the MSSM, you do not have any additional CP violation except this lambda 5 coupling in here. And EDM constant actually is pretty stringent. You will get killed by EDM constant.
Okay. So the reason I have asked because for gut baryogenesis we kind of know what kind of CP violation we need. The epsilon by G star is your YB. So epsilon is of the order of 10 to the minus 8. To generate those kind of numbers, we need gut scale bosons.
So, yeah, but you have not also seen proton leakage. So there are some strong limits on that baryogenesis. So because of non-observation of proton leakage.
So, right? So here, so I see there are many more degeneracies solely from the cosmology. So that's why you need collider constraints and other constraints.
Yeah. If you just satisfy this number, nobody knows. I mean, this number can be satisfied by maybe infinitely possible models. But if you, we have to assume a model and then test that model based on what we assume.
Okay, that's fine. Thank you.
Okay, good. So, any other questions?
Hello, can you hear me?
Yeah, I can hear you.
I am asking Tanmoy. So, you have commented that the cosmic inflation prefers nearly degenerate mass spectra. So, I was just wondering, since you are doing this Earth-studied inflation, so cosmic inflation observables would restrict the only quartic coupling of the second Higgs doublet. So how did you reach at this conclusion? You require nearly degenerate mass.
Sorry, I cannot see your face. So can you please?
No, the camera is not there. So I mean.
No. So what is your name? So I can't see because I'm seeing the screen. So
I am Abhijit.
Oh, hi. So you want to know why this nearly degenerating?
Yeah, since cosmic inflation should restrict the self-quartic coupling only, as far as I know.
Okay. It's because of running. Let me just go. Okay, so you see this here, right?
Right.
So this is the action written in Einstein frame, and your V is basically the potential, essentially the Higgs potential. Okay. you have this V rho 1, rho 2, rho 3 is basically Higgs potential with the quadratic coupling. The rho are basically field values. Isn't there how you pseudo-scalarity even Higgs also? Okay. But
So,
these
so
field values
which one is the inflator here?
depends on what your initial condition is. In our case, we took phi to be very large, so it's basically this is the inflator in our case, but these rows could be also inflator depending on the initial value. So we took rows to be pretty small, but that is not the reason why you have near degeneracy. You look at this V. This is I showed in previous slides. This is proportional to quadratic couplings of the Higgs boson. Okay? And you see the masses are also quadratic couplings. Okay? So these are dependent on quadratic couplings, and there is a common factor mu2 to square. And this mu2 to square sets the scale. But we took this roughly TeV scale, okay, for mu2 to 200 to 800 GeV. So we randomly generated mu2 from 0 to 1 GeV. And so we generated billions and billions of points, and for that, and so this is generated. You have to first check perturbativity, unitarity, and positivity condition at electric scale, and also you have to satisfy precision electric measurement like STU parameters. So we did that, and you have to take those coupling values and run them to the inflationary scale, which is roughly 10 to the 13 GeV or so, giga electron volt. Okay? So you have to run this coupling from electric to very high scale. And as you know, RG running, if your coupling values are large at electric scale, it goes to non-perturbative regime pretty quickly. Okay. So what we did, we forced them for numerical, since our computational facility is finite, so we just assume that these quadratic couplings are pretty small at electric scale, roughly about less than 1. And then we ran this coupling by RG equations to inflationary scale. So if you have small coupling at electric scale, you essentially can see this V square part is very, very less important because the cancellation and these couplings are very small. So essentially, the small value of this quadratic couplings, eta 3, eta 4, and all eta 1, eta 5, they set the mass of the Higgs boson and one common factor mu2 to square. And this part is very, very small. So that means the degeneracy between the masses, the factors that basically makes this masses degenerate is very small.
So you are saying mu2 is linking the two low energy physics and the inflationary physics, right?
Right. You can choose this at inflationary scale, which is fine. But
yeah. So as I see, the inflationary potential is leading by the second term in VE, right?
Sorry.
Inflation is leading by the second term in VE.
Inflation you have also here as well.
Oh, I see. Okay, got it.
And it's also not that. I mean, you have this rho 1 square here, and you have a rho 1 square, which is eta 1 square phi to the power 4 type of term. So you can see this is square, so it would be to the power 4. And you have to take this thing and you have to assume that quadratic coupling, that combination of this xi1 on m Planck squared or xi1 on square by m Planck to the power 4 times whatever your eta 1 square was, that factor multiplying in this one has to be greater than 0 at unitarity scale or at inflationary scale. So that is one additional condition.
Right.
And if you imply that is also restricting to be how large your coupling could be, and what we assume that it should be less than pi because of the perturbative limit. So it's not directly connected to inflation. It has that the requirement of RG running from electric scale to high scale. But it is a requirement for inflation. That's why we say that it's kind of emerging from a requirement of inflation. So you can see this number. Probably I have this slide. Okay, here. So this is the low scale value. This is the low scale value of these couplings. And if I run them in RG at high scale at 10 to the 13 GeV, roughly you have this quadratic couplings, this value. I put it 6 digit because during RG running, if you know, it is very much dependent on the decimal place, right? I mean, if you change the number at high scale, it will reach also.
But did you take the Coleman-Weinberg collection, because the couplings are pretty large here, as I see?
Which Coleman-Weinberg collection?
To the inflationary potential?
No. Why?
These couplings looks pretty large to me.
Why? What Coleman-Weinberg connection?
I mean this additional fields induce potential, inflationary potential.
So what do you mean by Coleman-Weinberg potential?
I mean the one
One loop
generated
corrected potential.
right.
That is already taken care of this Argirani, right? That is precisely
Oil. Yes, true.
Are you talking about temperature dependence?
No, I'm not talking about that.
Because the temperature is much, I mean, the field values are much higher than the electric field.
Right. Exactly. Another thing is the inflation potential turns out to be Starobinsky one, right?
For you are talking about in this one?
Right.
No. We took both of these things. So one is you can see the first one you can see essentially Starobinsky type of thing, and this is
Okay.
this one.
Okay.
But there are many issues with this Higgs after inflation. Kind of.
Okay.
জোর করে প্রশ্ন করতে হবে
There's some problem with the isotopic. Okay, so there
Yes.
আর করতে হবে না প্রশ্ন
Yes. Thank you.
আমি বললে তো হবে না বাবা
Any other questions? Students? Okay, so it seems there are no other questions. So let us thank Tanmoy.
Okay, so thank you for arranging the talk in such a short notice. So yeah.
Okay.
Okay. See you then.
Yeah. Bye.
Okay. Bye.